just to finish up with studying relationship between two variables or bivariate data. Okay, we have talked about correlation between two variables. We've talked about making using a least squares regression line, and then from that we talked about residuals, as well as the details and how to interpret the main parts of a least squares regression line, and actually what a least squares regression line is. So we never really talked about how to make the equation, and we're not going to do it by hand because that goes well beyond this course. So we're going to make equations of least squares regression lines using our graphing calculator, as well as using technology output, which you'll always be given. Anyway, to start, we finished off the last lesson by talking about outliers and the effect they had on certain measures, like R squared and R and S, okay? When you make the equation of a least squares regression line, you always need a point and the slope to make the equation of a line, okay? One point that is on any least squares regression line equation is the mean of the X and the mean of the Y, okay? So in this example, going back to our grocery store where we had average income versus organic items at a local grocery store, one of the points on the regression line when we want to create the equation for it will be the mean of the average income, comma, the mean of the number of organic items. So in this example, it was calculated 69,198 for the mean average income, so probably around there. And you can see that matches up with a mean of 52 items. Okay. So 1 point on the regression line would be X bar. Remember, bar stands for mean on the Y bar. And you actually find the slope using standard deviation. But like I said, we're not going to do this by hand. We're going to use a graphing calculator to help us. Just to talk more about certain points in a scatter plot. We talked about outliers. There are also some other points that can have an impact on certain measures of the least squares regression line and other measures. Something called low leverage. Low leverage points, remember, this is the original line, okay? Low leverage points are when we take out points around the mean of the explanatory variable. So notice anything around here was taken out. So low leverage points are close to X bar. What kind of impact does that have on the line? Well, if you look at this line and this line, you can see it doesn't change very much. Okay, it looks pretty close to the same slope and y-intercept. If the y-intercept below 20, slope climbs up about the same angle. A high leverage point, however, and this is not an outlier, this is different. Remember, an outlier is far from the line. Okay, high leverage points are far from X bar, but they're still part of the line. So these would be high leverage points. So they're far from the mean of the explanatory variable. And if we took them out, I'm going to try and keep both of these graphs on here. It did make a difference to the line. Notice the y-intercept went down even more. And if the y-intercept goes down even more, that means the line's tilting like this, so the slope is getting steeper. That's what I meant to say. Okay? So that's what leverage points do. High leverage points will change the slope and y-intercept of a line if they're taken out. Outliers will change R, R squared, and S. All of them, leverage points and outliers, we call influential points, meaning they can have some type of influence on the measures related to the least squares regression line. So we just talked about a high leverage point, that it's part of the line, but it's far from the mean of the explanatory variable. So when we take out a high leverage point, it's going to change the slope and y-intercept. When we take out an outlier, like this, doesn't really have an impact on slope and y-intercept, but it will change the standard deviation of the residuals, the correlation coefficient, as well as the correlation coefficient squared. If it's both, far away horizontally from the mean and well above or well below the line, it changes everything. All five measures: slope, y-intercept, S, R, and R squared. Okay. But like I said, we're not going to find equations of these lines manually. We're going to use our graphing calculators. Okay. So as an example, and you will be responsible for how many times you use this using your graphing calculator. Here we have some data. And we've got two variables: the weight of a stand mixer and the price of a stand mixer. Okay. I have to enter those lists in my graphing calculator. Do you remember how to do it? What button you go to get to the lists? Stat. Edit. You may already have numbers in there from what we did before. So if you want to clear those numbers out in one shot, highlight L1, hit clear, and enter. And it'll take out all the numbers. Highlight L2, hit clear, and enter. It'll take out all those numbers. So in L1, list these 6. 43, 28, 19, 17, 25, 26. Don't forget to hit enter after the last one you put in. Then in the second column, L2, list the prices. So 180, etc. Okay, so we've got all the data in. Now, punch stat again. And this time we want to scroll across to calc because we want to calculate the line. And we want to use linear regression, but not number 4, because number 4 is in the wrong form. So you need to scroll down to number 8. Linear regression A plus BX. Hit enter. It'll ask you to confirm, are you using list 1, list 2, leave the other 2 things, freak list and store required regression equation blank, highlight calculate, and you get 4 values. Okay? You get the y-intercept first, A, which should be 38.6. You get the slope, B, which should be about 9.56. You get R squared, and you get the correlation coefficient of 0.5, which means somewhat strong. Okay. So how do we write the equation? Well, we've got to write it in the form y equals a plus bx, but remember, we don't just write y. What do we write? Y hat. Because remember, it's the predicted price. These are the actual prices. Whoa. These are the actual prices, but when we make the equation, we're making a predicted price. So y equals a, which is 38.6 or 38.56, matter, plus 9.6 or 9.56. Again, doesn't really matter. The correlation coefficient is, we'll just say 0.49. And the correlation coefficient squared is about 0.24. And remember what that, you have to remember what that R squared means. It means 24% of the variation in price can be accounted for by weight of the stand mixer. We talked about that in the last lesson. Okay. So you should be able to, and I think actually you can, let's see. No. That didn't help. Sorry, just give me a second. Oh, I didn't turn it on. No, I'll have to look at that. Okay, we'll leave that for the time being. So that's how you're going to have to create a least squares regression line, the actual equation. Finally, other times you'll be given information about all those measures we've been talking about related to the least squares regression line. S, R squared, we can figure out R if we know R squared, slope, y-intercept, and generally it will look like this. This would be called a regression table, computer output. Okay? So how do we read this? Well, constant, if you think of constant, it doesn't have a variable, which means this is the y-intercept. Okay? Right below it, this is the slope. So just by looking at these two first numbers in the column under coefficient, we can create the line, the equation of the line. So it would be y hat equals negative 14.7 plus 0.001 x. We can also get other measures. Here, obviously, is little s, the standard deviation of the residuals. Here is R squared. Which is the correlation coefficient squared, which tells us how much the percent of, I always get this fumbled up too, the percent of variation in the y variable that can be explained by the x variable.
And remember, we usually express this as a decimal. So it'd be 0.617. So we could say here, S is 17.56.
That's sort of the typical distance. Each point is away from the least squares regression line.
R squared, I just referred to what it meant. Now you got to be very careful and take note of this because you've got to show this.
If I know R squared, I can calculate R by doing what?
Not quite.
How do you solve a quadratic equation like this? You do not take the square root, you take the positive and negative
Square root. So R is equal to plus minus 0.617.
That's important because if the slope is positive, it's going up, right? Which means R will be positive. If this was negative, your answer here for R would have to be negative. So it's important that you do plus minus.
Well, this tells me the slope is positive, so it's climbing up. So I don't need the negative.
It's plus whatever the square root of 0.617 is. Okay? Be aware of that.
Okay. And just to finish up,
We can possibly use prediction as discrimination. So this is our grocery store example again. We were given the least squares regression line equation. It was I want to make sure we have it. I think it's from the previous lesson. I don't think it's here. Anyway, the equation was y hat equals negative 14.7 plus 0.001x. That was the regression equation. So here's what you're asked. They're looking at opening two new stores, one in the lower income area, one in the higher income area. And in the lower income area, the actual mean income is 35,000. In the higher income area, the mean is 115,000. So based on the equation of this line, how many more organic items are predicted to be offered at the location in the higher income neighborhood? Well, all we have to do is find the number of organic items for the low by plugging 35,000 into the equation and calculating. And then find the predicted number of organic items in the high income neighborhood by using the exact same equation, except plugging in 115,000. Okay. So when you do that, might as well round it to the nearest whole number. We get approximately 20 items. Organic items will be offered in the lower income new location. And approximately 100 items, organic items, will be offered in the higher income location. Therefore, 80 more items will be offered in the higher income location.
One final question, and then this relates to the
Discussion actually in this lesson. Is this discrimination? Give me your opinion. Opinion means it's not right or wrong. Can you support it? Only 20, like organic items are generally considered healthy, right? So in this new low income store, there's only 20 items, but in the high income store, there's 100, Zara.
I mean, I would say it's discrimination in the way that it's not offering them healthy options, which kind of goes hand in hand with like obesity rates. If there was some statistics back in the obesity rates, each state, right? I'm sure that was shown. So it's kind of just not fair.
And I think that would be the common opinion. Likely. Who wants to argue against it? Because you could make an argument against it.
I was just saying that since people can be able to afford it, they'd just be losing money, but yeah.
And wasting food.
we're waiting for-
Right, because they wouldn't be able to sell it, it would all expire. Right, so really, it's hard to say. In like, this is what happens sometimes when we're asked for an opinion and trying to support it by facts. Well, you can kind of support this one both ways. That yes, it's discrimination because low income people are not getting access to all the healthy items high income people are, but no, it's not discrimination because, I mean, they're getting access to some healthy items, but they couldn't afford more healthy items. So therefore all that food would go to waste. Good. Yeah, well done. Okay.
I'm not sure